Picture a world shrouded in mystery, where humanity stood bewildered by the most fundamental questions about our universe. In this world, no one could explain why objects fall to the ground or why rain descends from the clouds. People gazed at the night sky, puzzled by an even greater mystery. Why doesn't the moon come crashing down to Earth? What invisible force keeps the planets moving in their celestial dance around the sun? Until the 17th century, these questions remained unanswered, leaving philosophers and scientists in a state of perpetual wonder. What if I told you that one of the greatest scientific revolutions in human history began with something as simple as an apple falling from a tree? This seemingly mundane event would spark a chain of thoughts that would forever change our understanding of the cosmos. Our story revolves around a solitary, introverted young man named Isaac Newton, whose brilliant mind would unlock the secrets that had eluded humanity for millennia. In the quiet contemplation of his garden, Newton would achieve something extraordinary. He would not only explain why things fall, but reveal the universal principles governing all motion in the cosmos. From the gentle descent of autumn leaves to the majestic orbits of distant planets, Newton would discover that a single set of mathematical laws could explain it all. His insights would unify our understanding of earthly and celestial phenomena, something no one had achieved before. This is more than just a story of scientific discovery. It's a testament to human ingenuity and the power of careful observation combined with deep analytical thinking. Newton's revelation would demonstrate that the universe operates according to precise, knowable rules that we could understand through the language of mathematics. This profound realization would forever transform our relationship with the natural world, showing us that the mysteries of the cosmos were not beyond human comprehension, but rather waiting to be uncovered by those who dared to look deeper. In the depths of rural England, during the tumultuous year of 1643, while civil war raged across the nation, a remarkable life began in the most humble of circumstances. On Christmas Day, in the modest manor house of Woolsthorpe, Lincolnshire, Isaac Newton entered the world prematurely. He was so incredibly tiny that, according to contemporary accounts, he could fit inside a quart mug. His survival seemed improbable. The midwives and his mother doubted he would live through his first day. Yet this fragile infant would grow to become one of history's most influential minds. Newton's early life was marked by profound loss and isolation. His father, also named Isaac, had died 3 months before his birth, leaving the family's modest estate to his unborn child. His mother, Hannah Ayscough, would soon remarry, leaving young Isaac in the care of his grandmother. This early abandonment would leave an indelible mark on Newton's character, perhaps contributing to his lifelong tendency toward solitude and self-reliance. Growing up in the solitude of Woolsthorpe Manor, young Isaac displayed an extraordinary curiosity about the world around him. While other children played traditional games, Newton spent countless hours crafting intricate mechanical toys, building working models of windmills and creating ingenious water clocks. His mind seemed constantly engaged in unraveling the mysteries of mechanical devices. He would meticulously observe the movement of the sun by driving pegs into walls to track shadows, creating what were essentially primitive sundials. In his youth, Newton showed little promise as a conventional student at the local village school. However, his uncle, recognizing something special in the boy, convinced Newton's mother to send him to grammar school in Grantham. There, while boarding with the local apothecary, Newton began to truly flourish intellectually. He would often forgo play with other students, preferring instead to read, experiment, and build mechanical devices in his room. As Carl Sagan so eloquently observed, Newton was a solitary by nature, but his solitude allowed him to dive deep into his thoughts. This natural inclination toward isolation, rather than hindering him, became the fertile ground from which his greatest ideas would spring. In his solitude, young Newton developed not just his intellectual capabilities, but also the capacity for intense concentration and prolonged contemplation that would later enable his groundbreaking discoveries. His childhood bedroom walls were covered not with the typical decorations of youth, but with intricate drawings of mechanical devices, mathematical equations, and careful sketches of natural phenomena. These early manifestations of his genius showed a mind that was already beginning to grapple with the fundamental questions of the universe, though the answers would come years later. This formative period of Newton's life laid the groundwork for his future achievements. His isolation, though perhaps painful on a personal level, created the perfect environment for his unique genius to develop. The young boy who seemed unlikely to survive his first day would grow into a man whose insights would fundamentally transform our understanding of the universe, proving that sometimes the greatest strengths can emerge from what might appear to be early disadvantages. In 1665, a catastrophic event that would paradoxically lead to one of the most remarkable periods of scientific discovery in history began to unfold. The Great Plague swept through England, forcing Cambridge University to shut its doors, sending its students and faculty fleeing to the safety of the countryside. Among them was a 23-year-old Newton, who returned to his family estate at Woolsthorpe Manor. What might have seemed like a devastating interruption to his studies would instead become what is now known as his annus mirabilis, the miracle year. During the following 18 months of enforced isolation, Newton's mind exploded with creativity and insight. Free from the rigid academic curriculum and daily distractions of university life, he embarked on what would become perhaps the most productive period of self-directed study in scientific history. In this rural solitude, with only his thoughts and observations to accompany him, Newton laid the groundwork for revolutionary advances in multiple fields of science and mathematics. Within the quiet walls of Woolsthorpe Manor, Newton began to develop his theories of calculus, which he called fluxions. This mathematical breakthrough would provide the tools needed to describe motion and change in precise mathematical terms, something that had eluded mathematicians for centuries. Working alone, with no one to challenge or validate his ideas, he created a new branch of mathematics that would become essential to scientific progress. During these same months, Newton began his groundbreaking work on optics. In his darkened room, he bored a small hole in his window shutters and used a prism to split sunlight into its spectrum of colors. This simple yet ingenious experiment led him to understand that white light was actually composed of all the colors of the rainbow, a revelation that would fundamentally change our understanding of light and color. The isolation imposed by the plague created what Newton would later describe as the most productive and creative period of his life. Without formal books or academic guidance, he was forced to rely on his own observations and mathematical reasoning. This independence from conventional wisdom may have been crucial in allowing him to make such revolutionary breakthroughs. The intensity of Newton's work during this period was extraordinary. His notebooks from this time reveal page after page of calculations, diagrams, and theoretical musings. He would often become so absorbed in his work that he would forget to eat, and his servants would find his meals untouched outside his door. This level of concentration and dedication would have been nearly impossible in the bustling environment of Cambridge. Most remarkably, during these months of solitude, Newton began to formulate his early ideas about universal gravitation. While the famous apple incident may or may not have occurred exactly as legend suggests, it was during this period that he began to seriously consider the force that pulls objects toward Earth and its potential relationship to the forces governing celestial bodies. When Cambridge reopened its doors in 1667, Newton returned with a wealth of revolutionary ideas that would transform science. The enforced isolation of the plague years, though tragic in its broader context, had provided the perfect incubator for Newton's genius to flourish. This period stands as a testament to the extraordinary potential of the human mind when given the time and space to explore, contemplate, and create. This chapter in Newton's life reminds us that sometimes the most significant breakthroughs can come during periods of solitude and reflection. His miracle year demonstrates how isolation, though challenging, can become an opportunity for deep thought and revolutionary discovery. It shows us that the power of the human mind, when focused and unencumbered by daily distractions, can achieve extraordinary things. The story of Newton's apple is perhaps one of the most famous anecdotes in the history of science, often dismissed as mere legend. However, contrary to popular skepticism, this pivotal moment is well documented in Newton's own writings and confirmed by his contemporaries. In his later years, Newton recounted to several witnesses, including his niece, Catherine Conduit, how watching an apple fall in the Woolsthorpe garden sparked a chain of thoughts that would revolutionize our understanding of the universe. As Newton himself described it, he was sitting in contemplation in the garden when he observed an apple falling straight to the ground. This ordinary event triggered an extraordinary question in his mind. Does the force that pulls the apple downward extend beyond the Earth's surface? If so, how far does it reach? Could it extend all the way to the moon? This series of questions led to what might be considered one of the greatest intellectual leaps in scientific history. The revolutionary insight came when Newton connected two seemingly unrelated phenomena, the falling apple and the moon's orbit around Earth. He realized that the moon's circular path could be explained if it was constantly falling toward Earth, just like the apple, but with its forward motion precisely balanced against this falling force. This was a stunning conceptual breakthrough. The idea that terrestrial and celestial mechanics could be governed by the same fundamental force. To test his theory, Newton embarked on a mathematical journey of unprecedented sophistication. He calculated that if his theory was correct, the force keeping the moon in orbit should decrease with the square of its distance from Earth. Initially, his calculations didn't quite match observations, leading him to temporarily set aside the work. Years later, with more accurate measurements of Earth's size, he returned to these calculations and found they matched his theory perfectly. Stephen Hawking's observation that Newton showed us that the universe operates under precise and universal mathematical laws captures the profound significance of this discovery. For the first time in human history, someone had demonstrated that the same mathematical principles could explain both earthly and celestial phenomena. This unified view of nature was revolutionary. It suggested that the universe wasn't governed by mysterious or divine forces, but by mathematical laws that could be discovered and understood. The implications of this insight were staggering. If the same force that caused an apple to fall also kept the moon in orbit, then this force must act throughout the entire universe. This led Newton to his universal law of gravitation, the idea that every particle of matter in the universe attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. This unification of terrestrial and celestial mechanics shattered the ancient Aristotelian division between earthly and heavenly phenomena. No longer were the heavens governed by special, perfect laws, while Earth operated under different principles. Newton showed that a single set of mathematical laws governed everything from falling apples to orbiting planets, from ocean tides to the paths of comets. The apple story, far from being a simple tale of sudden inspiration, represents a moment when careful observation met mathematical reasoning to produce one of science's greatest insights. It demonstrates how a seemingly mundane event, when viewed through the lens of genius, can lead to profound universal truths. Newton's ability to see the cosmic in the commonplace, to connect the fall of an apple to the orbit of the moon, exemplifies the power of scientific thinking at its most brilliant. This episode also illustrates Newton's remarkable ability to move between the practical and the theoretical, from concrete observation to abstract mathematical reasoning. The apple provided a tangible starting point from which he could build a mathematical framework that explained the mechanics of the entire universe. It was this combination of observational insight and mathematical rigor that would characterize his greatest contributions to science. Newton's formulation of universal gravitation stands as one of the most elegant and powerful theories in the history of science. In its mathematical form, this law states that every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This simple yet profound equation, F, G, M2, R2, would transform our understanding of the cosmos forever. The revolutionary aspect of Newton's law lay in its universality. For the first time, someone had demonstrated that the same mathematical principle could explain an enormous range of phenomena. From the gentle descent of a leaf spiraling to the ground to the majestic sweep of comets through the solar system, all could be understood through this single equation. The falling leaf, though affected by air resistance, ultimately follows a path dictated by Earth's gravitational pull. The same force, scaled up to astronomical proportions, keeps the moon in its orbit and binds the planets to the sun. Newton's mathematical framework proved remarkably precise in predicting planetary motions. Using his equations, astronomers could calculate the exact positions of planets months and even years in advance. This predictive power extended far beyond known phenomena. When astronomers noticed perturbations in Uranus's orbit that couldn't be explained by the known planets, they realized these irregularities must be caused by the gravitational pull of an undiscovered world. This led to the mathematical prediction and subsequent discovery of Neptune in 1846, almost 120 years after Newton's death. The implications of universal gravitation reached even further. Newton's laws explained the ocean's tides as the combined gravitational effects of the moon and sun on Earth's waters. They accounted for the slight bulging of Earth at its equator, caused by the planet's rotation against its own gravitational field. Even the precession of Earth's axis, a phenomenon known since ancient times, could now be understood as a gravitational effect. Perhaps most remarkably, Newton's theory showed that gravity, while appearing weak in everyday experience, becomes the dominant force shaping the universe at astronomical scales. It explains why stars form from vast clouds of gas, why galaxies hold together, and why the cosmic web of matter has the structure we observe. The same force that causes an apple to fall to Earth also shapes the largest structures in the observable universe. Newton's mathematical description of gravity would remain unchallenged for over 2 centuries, until Einstein's theory of general relativity provided a deeper understanding of gravitational forces as curvatures in space-time. Yet even today, Newton's equations remain sufficiently accurate for most practical purposes, from calculating satellite orbits to planning interplanetary missions. His insight that the universe operates according to precise mathematical laws, discoverable through careful observation and reasoning, fundamentally changed humanity's relationship with the cosmos. The ultimate triumph of Newton's universal gravitation was not just its ability to explain observed phenomena, but its power to predict new discoveries. It showed that through mathematical analysis, we could uncover secrets of the universe that lay beyond our immediate observation. This legacy continues to inspire modern physics, where mathematical beauty and consistency often guide us toward new insights about the nature of reality. Newton's legacy extends far beyond his theory of universal gravitation, encompassing fundamental laws of motion, revolutionary advances in optics, and the development of powerful mathematical tools. His contributions continue to influence science and technology centuries after his death, forming the bedrock of modern physics and engineering. The 3 laws of motion that Newton formulated in his masterwork, Principia, revolutionized our understanding of the physical world. The first law, often called the law of inertia, states that an object will remain at rest or in uniform motion unless acted upon by an external force. This seemingly simple principle challenged the prevailing Aristotelian view that objects naturally came to rest, revealing instead that rest and uniform motion are equivalent states requiring no explanation. His second law, expressing that force equals mass times acceleration, FRMA, provided a precise mathematical relationship between force and motion. This elegant equation became the foundation for classical mechanics, enabling engineers and scientists to calculate exactly how objects would move under various forces. From the design of modern aircraft to the planning of space missions, this fundamental relationship continues to guide technological advancement. The third law, stating that for every action there is an equal and opposite reaction, completed this revolutionary trilogy. This principle explains everything from the recoil of a fired gun to the thrust that propels rockets through space. These 3 laws together created a comprehensive framework for understanding motion that remained unchallenged until the advent of quantum mechanics and relativity theory in the 20th century. Newton's contributions to optics were equally revolutionary. Frustrated with the poor quality of refracting telescopes of his time, which suffered from chromatic aberration, he invented an entirely new type of telescope. His reflecting telescope used mirrors rather than lenses to gather and focus light, eliminating the color distortion that plagued earlier designs. This invention marked the birth of modern astronomical telescopes. Today's largest optical telescopes, from the Hubble Space Telescope to the giant observatories in Chile and Hawaii, are all descendants of Newton's original reflector design. Perhaps most profound was Newton's development of calculus, created to solve problems that existing mathematics couldn't handle. The fundamental insight of calculus, that complex changes can be understood by breaking them down into infinitesimally small steps, provided a powerful new tool for describing and analyzing motion, change, and continuous processes. Newton's method of fluxions, as he called it, became the mathematical language of science and engineering. The impact of calculus extends far beyond physics. In modern times, it's essential in fields Newton could never have imagined. From modeling climate change to analyzing economic trends, from designing computer graphics to understanding population dynamics. Every time an engineer calculates the optimal shape of an airplane wing or a scientist models the spread of a disease, they're building on Newton's mathematical innovations. Newton's development of calculus also introduced the concept of rates of change, which revolutionized how we think about dynamic systems. His work on infinite series, differential equations, and mathematical analysis laid the groundwork for countless developments in pure and applied mathematics. The notation and methods he developed, refined by later mathematicians, remain central to mathematical education and practice today. Newton's legacy also includes less celebrated but equally important contributions. His work on fluid dynamics helped establish the principles governing fluid flow. His studies of light and color revealed the spectrum of visible light and laid the foundation for modern optical science. Even his careful experimental methods, documented meticulously in his notebooks, helped establish the standards for scientific research. The true measure of Newton's legacy lies not just in his specific discoveries, but in how he transformed the very nature of scientific inquiry. He showed that complex natural phenomena could be understood through careful observation, mathematical analysis, and logical reasoning. His approach, combining theoretical insight with experimental verification, became the template for modern scientific method. More than 3 centuries after his death, Newton's influence persists in unexpected ways. The algorithms that guide autonomous vehicles use his laws of motion. The telecommunications satellites orbiting Earth rely on his gravitational calculations. The computer simulations that model everything from weather patterns to galaxy formation build on his mathematical innovations. As Einstein noted, Newton's clear and wide-ranging ideas will forever retain their significance as the foundation on which our modern conceptions of physics have been built. His legacy reminds us that fundamental discoveries, though centuries old, continue to shape our understanding of the universe and our ability to interact with it. In the endless chain of scientific progress, Newton forged some of the strongest and most enduring links. Isaac Newton's legacy extends far beyond his specific scientific discoveries. His greatest gift to humanity was demonstrating that the universe operates according to rational principles that we can understand through careful observation, logical reasoning, and mathematical analysis. This revelation marked a pivotal moment in human intellectual history. The realization that the cosmos isn't governed by mysterious or arbitrary forces, but by precise, comprehensible laws. Newton showed us that the same principles that explain everyday phenomena can unlock the deepest mysteries of the universe. His work bridged the gap between the mundane and the cosmic, revealing that the fall of an apple and the orbit of planets are manifestations of the same fundamental law. This unification of terrestrial and celestial mechanics destroyed the ancient notion that heavenly bodies followed special, unknowable rules different from those governing Earth. Perhaps the most inspiring aspect of Newton's story is how it demonstrates that profound discoveries can emerge from simple observations. The key lies not in the complexity of the phenomenon being observed, but in the depth of thought applied to understanding it. Newton's contemplation of a falling apple led to insights about universal gravitation, not because the apple's fall was particularly special, but because he possessed the curiosity and intellectual rigor to ask deeper questions about what he observed. His famous quote, "If I have seen further, it is by standing on the shoulders of giants," reveals another crucial aspect of scientific progress, the importance of building upon previous knowledge while remaining humble enough to acknowledge our debt to earlier thinkers. Newton, despite his towering genius, recognized that his achievements were possible only because of the groundwork laid by previous generations of scholars and philosophers. Newton's work established a template for scientific inquiry that continues to guide researchers today. His combination of careful observation, mathematical analysis, and theoretical modeling showed how we can move from specific observations to universal principles. This methodology has proven remarkably successful, leading to countless discoveries across all fields of science. The enduring power of Newton's insights reminds us that true scientific understanding doesn't become obsolete. While our knowledge has expanded far beyond what Newton could have imagined, his fundamental contributions remain relevant. Modern physicists may use more sophisticated mathematical tools, and deal with concepts Newton never dreamed of, but they still build upon the foundation he established. As we conclude our exploration of Newton's remarkable life and achievements, we're reminded that the pursuit of knowledge is an ongoing journey. Each generation builds upon the discoveries of the past, pushing the boundaries of human understanding ever further. Newton's story inspires us to maintain our curiosity about the world around us, to think deeply about what we observe, and to never stop questioning. And now, if you found yourself as captivated by this extraordinary journey through Newton's life and discoveries as we have here at Exploring the Universe, we invite you to join our community of cosmic explorers. By subscribing to our channel and activating notifications, you'll ensure you don't miss any of our future adventures into the mysteries of the cosmos. Remember, every great scientific journey begins with curiosity and wonder. The same curiosity that led Newton to question why an apple falls and why the planets move as they do. Together, we can continue this tradition of exploration and discovery, pushing the boundaries of human knowledge ever further into the vast expanse of space and time. Join us as we continue to unravel the mysteries of the universe, one discovery at a time. Hit that subscribe button and turn on notifications to become part of our growing community of science enthusiasts. Because in the grand tradition of Newton, we're all standing on the shoulders of giants, reaching out to touch the stars. Let's explore the cosmos together. There's still so much to discover.